So here's a very common type of engineering application of differentials. Suppose that we're going to machine a block, so a block of wood, metal, some part for a device, and it's supposed to be 3 by 4 by 6, but it's important that the volume be 72 accurate to within say 0.1. Okay, so the idea is that there's some accuracy that needs to be attained here, because nothing is exactly perfectly right on the nose in the real world. You're always off by some little fudge factor due to whatever the kerf or whatever dust you lose making the cut. Okay, so the question is then, if the error, like how accurate do you have to be in measuring the side lengths and getting the side lengths cut exactly for the right dimensions in order to get the volume within the required tolerance, right? And so let's suppose that we're using the same ruler to measure the x and y and z dimension. So if the error measuring each dimension is the same, then what accuracy, so how accurate does it need to be? What accuracy is required to satisfy this constraint? In other words, of being within 0.1 of the desired volume. Okay, so let's see. So the volume for a block with sides x, y, and z is just the product of those standard volume for a rectangular solid, and we're looking at the point 3, 4, 6 for our inputs, and we're going to take the x discrepancy and y discrepancy and z discrepancy all to be equal. So this is the error measuring each dimension. Let's call it epsilon. Okay, and then we want to find some constant c such that which acts as a bound on how bad our error can be. So in other words, as long as our inaccuracy is less than c, then we have that the measurement of our differential is bounded by 0.1. That's what we want. Okay, so let's see. So if we compute the differential, so this is going to be v sub x dx plus v sub y dy plus v sub z dz. So we look at the partial of v with respect to x, and it's yz, and the partial of v with respect to y is xz, and the partial of v with respect to z is xy. All right, and so then let's see. So then if we evaluate, let's see. So y times z is 24, and x times z is 18, and x times y is 12, and then we also decided that each of these discrepancies is going to be equal. So this is epsilon, this is epsilon, and this is epsilon. And so if we add all those up, we get 54 epsilon. Okay, so now let's see. We want to have it be the case that our differential, so the inaccuracy of our final computed volume, is estimated by 54 epsilon, and we need that to be less than or equal to 0.1 because that's the constraint that we were given. And so then that tells us what our constraint on epsilon needs to be. So I'm just going to divide this 54 over to the other side here, and I find that the epsilon has to be bounded by 0.1 over 54, which is 0.0019, which is actually kind of tiny, right? I mean, this is small. So in order to get an accuracy of volume within 0.1 cubic units at the end, we have to have the linear measurements accurate to within 0.0019. So you gotta be pretty careful with your cuts in order to get the volume that accurate.